Good evening, students. Welcome to my 10th lecture on circuit theory. Today, let us continue discussing on circuit transients. Let us first start with the topic of charging a capacitor. Charging of capacitor means we need a charging agency. A DC source will act here as a charging agency. Okay. Now we will look how the how the current and resistance across various elements will vary. Okay, let us take the EMF of the voltage source as V. Okay, and the current through two elements let I, and voltage across C is Vc. So if we apply KVL in this loop, we will get IR plus Vc equal to what? Equal to V. And we know that I equal to what? I equal to C dVc dt. Okay. Now if we replace this I here, we will get RC dVc dt plus Vc equal to V. Let us divide both the sides by CR. So the equation will become dVc dt plus Vc by CR equal to what? V by CR. Now this is a first order differential equation, and this first order differential equation, the solution of this first order differential equation has two parts. One is CF and another is particular integral or PI. Now for CF, we will solve this equation dVc dt plus Vc by CR equal to 0. Now we are familiar with this equation. In the last lecture, we described this equation as natural response of RC circuit or discharging of a capacitor. Now we got Vc from this equation as A e to the power minus T by CR. Now A is initial condition. If the initial voltage across the capacitor is V0, so A equal to V0, so Vc equal to V0 e to the power T by CR. Okay, or Vc, the graph of Vc with T was like this one. Okay, in order to solve for Phi, now in order to solve for Phi, we have to solve this equation dVc dt plus Vc by CR equal to what? V by CR. Okay. Now from our previous discussion, you can recall that in order to solve this equation, we can imagine Vc as constant, Vc as k. So if Vc is a constant, then dVc dt equal to what? dVc dt equal to 0. So let us replace these two in this equation. So k by CR equal to V by CR, or k equal to V. Okay, so the complete solution of Vc is what? Complete solution of Vc equal to Ca plus Pi. Now let us add these two. Pi is V and Cf is this one. So Vc equal to V plus V0, V plus say A, V plus A e to the power minus T by Cr, where A is a constant and this constant can be determined from the initial condition. Now if the initial condition is 0, that is the voltage across the capacitor at t equal to 0 is 0. Now put t equal to 0, then Vc equal to 0, or initially relaxed capacitor was there. So 0 equal to V plus A e to the power 0. A e to the power 0 means 1, or A equal to what? A equal to minus V. If A equal to minus V, from this equation we will get Vc equal to V1 minus e to the power minus T by Cr, and that as Cr equal to time constant, so we can call it time constant lambda. Dot Vc against T, we will get this sort of waveform. The waveform will start from 0. The waveform will start from 0 at t equal to 0. You can check it at t equal to 0. Vc equal to V into 1 minus e to the power 0. E to the power 0 means 1. So Vc equal to 0. And when t equal to infinity, then this term will be 0. So Vc equal to V. So the final value of Vc equal to V. Okay. Now if Vc equal to this one, then I equal to what? I equal to C into dVc dt. I into C dVc dt. Now we know that current through C can be determined by C dVc dt. Now the expression of Vc is here. So dVc, C into dVc dt. C into ddt of what? ddt of V minus V e to the power minus T by Cr. Okay. So ddt of V is 0. We will not bother about V. Now this will be minus this minus is for this one, and e to the power minus T by Cr into minus 1 by Cr. Now this C and C will be cancelled, make it plus. So, one V will come here, minus V into this one. So the result is V by R e to the power minus T by Cr. Now let us call it I0. V by R is I0 e to the power minus T by Cr. So the graph of I will be like this one. This is exponentially decreasing function I with t. The initial value of I is I0 and the value of I0 is V by R. Now at t0, at t one time constant, what will be the value of voltage and current? At t equal to lambda or time constant Cr. Now you can check it after t equal to lambda. Vc will be 0.632 into V, okay, or 63.2% of the final voltage. So this is the time constant, this is the in time constant interval, we can call this interval as lambda, and we will get 63.2% of the final value. And at t equal to lambda, IC or I equal to 0.368 into I0, or 36.8% of initial current I0. Now pictorially we can represent this one, this is lambda and this is 0.368 of I0. Okay. Now these are all explained while discussing on charging or discharging of an inductor. Okay. At the time of discharging, these all are at the time of charging a capacitor. Then let us recall the graphs of discharging a capacitor. While discharging, Vc equal to V0 e to the power minus t by lambda, and I equal to what? I equal to C dVc dt, and C dVc dt means Vc equal to V0 e to the power minus t by Cr, or this is V0 minus Cr into C into e to the power minus t by Cr. Cc will be cancelled out and this will be minus V0 by R e to the power minus t by Cr, or minus I0 e to the power minus t by Cr, or t by lambda. So at the time of discharge, Vc will vary like this one, and I will vary, the I will change, like I will follow this path. This is I, and final initial value of I was minus I0. Okay. Now, so at the time of discharge, the voltage across the resistance will vary like this one. This is voltage across the resistance, and this will start from minus I0 into R. At the time of charging a capacitor, voltage across R will vary this in this path. This is I0 into R. I0 into R means V, and minus I0 into R means minus V. This is minus V. Okay. Now let us look what will happen if this RC circuit is excited by this nature of waveform. This nature of waveform. Okay. This is called a train of pulses. This is a pulse function, and this is called a train of pulses. Now, the supply voltage consists of these pulses. Okay. Now, this is the supply voltage, Vs supply voltage. This is V for some interval, and the supply voltage is 0 for some interval. Okay. Now in this interval, the capacitor will get charged, and in this interval the capacitor will get discharged. Okay. Now the voltage across the capacitor will vary in this way. Say initially the voltage let us now recall two equations quickly. One is, this is the phenomenon of charging a capacitor by a DC source. So here the voltage, the equation of voltage across the capacitance is given by what? Vc equal to V into 1 minus e to the power minus t by tau, where tau is, tau is time constant. Okay, now so Vc, the graph or plot of Vc will be like this one, okay, with t. Now when t tends to infinity, what will happen? E to the power minus t by infinity will become 0. So Vc equal to V. Vc equal to V means this voltage will appear across the capacitance. So it can happen only when current through R and C is 0, or if the capacitance will act as a open circuit. So at t equal to infinity or at steady state, the capacitance will act as open. Okay. Now if the charging agency is DC one. Now let us recall the equation of charging an inductor with the help of a DC voltage source, VRL. Here the equation I through R and L is given by what? V by R 1 minus e to the power minus t by tau. Here tau is the time constant of a RL series circuit and given by tau equal to L by R. Here also the nature of I with time is given by this graph, where this is V by R. Now at t tends to infinity, what will happen? E to the power minus t by tau will become 0. So I equal to what? V by R. Hence we can conclude that at t equal to infinity, the L will behave as a short. In this case only, I will become V by R. Okay, so the conclusion is at DC steady state, the inductor can be approximated as short and a capacitor can be approximated as open. This will behave as short and capacitor will behave as an open. Okay. Now in this context, let us solve this very simple but important problem. Here the problem statement is the switch has been in position 1 for a long time. And the switch is moved to position 2 at t equal to 0. Now we have to determine the current through the inductor IL at t greater than 0, greater than equal to 0. Now, in the problem, this is stated that the switch was in position 1 for a long time. Now, there is the operating voltage is DC1. So, for a long time means we will consider it for infinity. Okay. Now, for infinity amount of time, this circuit was there. The circuit was like this one. This is 40 ohm, this is 60 ohm, this is 50 ohm, this is 1 millihenry inductor, and this is a 100 volt source, DC source. Now, so for infinity number amount of time, this circuit was there. So one steady state was there. So in steady state, we can approximate this inductor as a short. Let us make it short. If this is shorted, then this 50 ohm resistance will be bypassed. That is, no current will flow in this flow through this 50 ohm. Therefore, the current through this inductor IL will be what? 100 by 60 plus 40 ampere, that is 1 ampere. Now, this is the current at t equal to 0. So, IL0 is equal to 1 ampere. Okay. This is, so the inductor was not initially relaxed. There was a initial current through the inductor. The amount of current is 1 ampere. Now at t equal to 0, the circuit condition was this one. From t equal to 0, the circuit condition was this one. This is the circuit from t greater than equal to 0. This is 160 ohm resistance, this is 40 ohm resistance, this is a 75 volt DC source, this is 50 ohm resistance, and this is 1 millihenry inductor. We have to make it a RL series circuit. We have to make it a RL series circuit. So, if this is the point A and this is the point B, from A and B, viewing from A and B, we have to replace this circuit by a Thevenin circuit, Thevenin's voltage source VTH and Thevenin's resistance RTH. In order to do that, we have to make this load or this inductor open. If we make this open, the voltage across A and B, that is VTH, is given by what? VTH is the voltage across the 50 ohm resistance. So in this circuit, the voltage across 50 ohm resistance is what? VTH equal to 50 into I. I means 75 by 40 plus 50, 60 plus 50, that is 150 volt, that is 25 volt. VTH is 25 volt. Now RTH, let us determine RTH. In order to determine RTH, we have to make this one shorted, this voltage source shorted, and we have to determine the resistance across A and B. The resistance across A and B can be determined by look, there is two paths. We can go from A to B in two paths, in two ways. One is through this one and another is through this one. So there are two parallel paths. One has 50 ohm resistance and another has 100 ohm resistance. So RTH is parallel combination of 50 and 100 ohm resistance. So this is 50 into 100 by 150 ohm. So this is 100 by 3 ohm resistance. Read on the Thevenin's equivalent circuit. So here the current through the inductor is IL. The operating equation, we know the operating equation of this type of circuit is given by what? Di dt plus Ri equal to what? V. Let us put IL. IL is current through the inductor. So DIL dt plus R by L IL equal to what? V by L. So this is a differential equation. This differential equation has two parts. We know that this differential equation has two parts. And IL is equal to what? IL is sum total of the complementary function and particular integral. For complementary function, in order to get the CF, we have to solve this equation DIL dt plus R by L IL equal to 0. This represents nothing but the natural response or discharging equation of the RL series circuit. And we know that IL is given by A e to the power minus R by L into T. Okay. Now for particular equation, the particular integral, we can imagine IL equal to K. So if we imagine IL equal to K, DIL dt equal to 0. So IL R by L into IL equal to what? V by L. So IL equal to what? V by R. Okay. Now V is what? V is 25 and R is 100 by 3. So 25 by 100 into 3. So this is what? 3 by 4. So the complete solution of I is equal to IL equal to A e to the power minus R by L into T plus 3 by 4. Now put T equal to 0. So IL 0 will become A plus 3 by 4. Now we have determined that IL 0 equal to 1 ampere. So A equal to 1 minus 3 by 4, that is 1 by 4. So let us replace this one, this A here. So IL equal to this is 1 by 4 e to the power minus R by L T plus 3 by 4. Now R was 100 by 3 and L was what? 1 millihenry. That is what? 1 into 10 to the power minus 3 Henry. So R by L is equal to 100 by 3 into 10 to the power minus 3. So 10 to the power 5 by 3. Hence, let us replace this one here. So IL equal to 1 by 4 e to the power minus 10 to the power 5 by 3t plus 3 by 4. This is the expression of current through the inductor at t greater than 0. Okay? Problem. That problem says that this is a circuit consisting of a single capacitor of capacitance value what 1 microfarad. Okay. Now the problem statement is the switch has been in position 1 for a long time and moved to position 2 at t greater than t equal to 0. Determine IC, or let us determine I. Let us determine I at t greater than 0. Okay. Now the circuit was in DC steady state. So we know that in DC steady state the capacitor will behave as an open. So the condition of the circuit was like this one: at t greater than 0, at t less than 0, the voltage source, the EMF of the voltage source was 100 volt, that is a 40 ohm resistance, 60 and 50 ohm resistance, and this we can treat the capacitor as a open. So the primary voltage across the capacitor at t equal to 0 can be determined by, this is equal to the voltage across 50 ohm resistance. So Vc0 equal to 50 into I, as V equal to IR. So I can be determined by, this is 100 by what? 150 ohm. So this is this much voltage, this much volt. So this is 100 by 3 volt. Now this is the condition of the circuit at t less than 0. Okay. Now from t equal to 0 or at t greater than equal to 0, the circuit will look like this one: 60, this is 60 ohm resistance, this is a 50 ohm resistance, this is 40 ohm resistance, this is 75 volt source, and there is a capacitor of capacitance 1 microfarad. So like the previous example, we have to replace this circuit by a RC series circuit. The R is the Thevenin's resistance and V is the Thevenin's voltage. The C is 1 microfarad capacitance. So RTH equal to, RTH was what? RTH was the combination, parallel combination of 50 and 100 ohm. So this was 100 by 3 ohm, and VTH was, I think VTH was 25 volt. 50 into 75 by 150 volt. This was 25 volt. Okay. I have just redrawn the RC series circuit and replaced the VTH and RTH by the exact values. VTH was 25 volt and RTH was 100 by 3 ohm. Now, the operating equation of a RC series circuit is given by what? RC dVc dt plus Vc equal to V, the forcing function, or dVc dt plus Vc by Rc equal to what? V by Rc. Now this is one differential equation. This can be solved by one CF and PI. For CF, in order to get the CF, we have to solve this equation, dVc dt plus Vc by Rc is equal to 0. So Vc equal to a e to the power minus t by Rc, and Pi, for Pi we have to assume Vc equal to k. So if Vc equal to k, then Vc will come as V. Okay. Now Vc equal to k means dVc dt equal to 0. dVc dt equal to 0. Now let us just replace these two here. So Vc equal to V. So the complete solution of Vc at t greater than 0 is a e to the power minus t by Rc, and Vc equal to V means 25 volt. In this circuit, V is VTH. VTH is 25. So Vc, complete solution of Vc is this one, 25. Now put t equal to 0. If we put t equal to 0, now Vc will become, Vc at t equal to 0 will become a plus 25. Now a plus 25 is the initial condition, 100 by 3. So a equal to 100 by 3 minus 25. So 25 25 by 3. So we can write Vc as a, replace a by 25 by 3, e to the power minus t by Rc plus 25. Now Rc, the value of Rc is, R was 100 by 3 and C is 1 microfarad, that is 10 to the power minus 6 farad. So this is equal to 10 to the power 4 by 3, 10 to the power 10 to the power minus 4 by 3. Therefore Vc can be written as 25 by 3 e to the power minus t by Rc, that is 3t, t by 10 to the power minus 4 by 3 plus 25. Let us take both at the numerator. So 25 by 3 e to the power minus 3 into 10 to the power 4 t plus 25. Okay. Now this is the equation of voltage across the capacitor at t greater than 0. If this is the voltage across the capacitor, so current through the capacitor is what? C into dVc dt. Now dVc dt equal to what? dVc dt equal to 25 by 3 into minus 3 10 to the power 4 e to the power minus 3 into 10 to the power 4 t. Okay, now 3 will get cancelled. Now c dvc dt equal to 1 into 10 to the power minus 6. This is the value of the capacitor, and the rest is, this is minus 25 10 to the power 4 e to the power minus 3 into 10 to the power 4 t. Okay, so this will become minus 25 into 10 to the power minus 2 e to the power minus 3 into 10 to the power 4 t. Okay, this is the current through the capacitor. Now current through the resistance, 50 ohm resistance is what? IR is VC by 50. Now VC by 50 means VC, the value of VC is this, so 25 by 50 means 1 by 2, and this is 1 by 6 e to the power minus 3 into 10 to the power 4 t. Hence the total current is I equal to IC plus R, IC plus IR, and IR is half plus this one into this one, means 1 by 6 minus 25 into 10 to the power minus 2, okay, e to the power minus 3 into 10 to the power 4 t. Okay, so this is the total current at t greater than 0. Okay, now let us discuss about two important things. RL circuit, in RL circuit, this L by R is called what? Time constant. Okay, this is the amount of some time. So the unit of tau equal to what? The unit of L by R. So we know that the unit of time is second. Okay, now the unit of L by the unit of R equal to the unit of time. How you can prove this one? Now we know that V equal to what? L di dt. So the dimension or the unit of inductance equal to the unit of voltage into the unit of time into the unit of current. Okay, on the other hand, we know that V equal to I into R. So the unit of resistance or the dimension of resistance equal to what? The dimension of voltage by the dimension of current. Okay, now let us divide this by this one. So the dimension of L by dimension of R equal to the dimension of V into the dimension of time by dimension of current into the dimension of current by dimension of voltage. Okay, so these will get cancelled. So this is the dimension of time. Okay, hence we can call that L by R, the unit of L by R is second. Okay, now in a RC circuit, the time constant is given by what? R into C. So the unit of RC, R into C, must be equal to the unit of time, that is second. Okay. Now this can be proved also by very easily. So we know that C dv dt equal to what? C dv dt equal to I. So the unit of C equal to the unit of current into the unit of time or dimension of time by dimension of voltage, and on the other hand the unit of resistance or dimension of resistance equal to what? V by I, as V equal to IR. Okay, so the unit of R into the unit of C equal to what? I into T by V into unit of V by unit of I. So these will get cancelled. So the unit of T remains. So the unit of RC, that is the time constant of the RC series circuit, equal to the unit of RC is second. Now with this, let us conclude for today. Okay. Now we will meet in the next class. Thank you.